for this program is provided by Annenberg CPD to advance excellent teaching.
I have a bit of a cold today, so I thought I might start out this morning by making myself a cup of tea. Obviously, that's going to be iced tea. Whether something is hot or cold depends on how you look at it. And yet, we all know that it's easy to make something warm, and it's really quite hard to make something cold. For example, we've known about fire ever since Prometheus let the secret slip long before the dawn of history. But the refrigerator is barely older than the oldest living person. Our job today is to find out how to go about making things cold. And incidentally, how cold is cold? The stuff in here is at a temperature so low that the very air itself becomes a liquid. Now that's really cold. Today, we're going to find out how to make that.
These extraordinary machines work wonders with the most common gas in the atmosphere, ordinary air. That's the raw material of this plant, the ordinary urban air of a modern industrial environment. These machines compress that air and necessarily heat it as well. The air is then cooled back down for the first time. And before these machines are finished with it, the same air will be compressed and cooled further and further, 4 times in all. And finally, inside this column, ordinary air, commonly an odorless and colorless mixture of mostly nitrogen and oxygen, will be transformed. Finally, it will be liquid. The air enters a configuration of filters, and in the process, before coming out as a liquid, its temperature has been lowered extremely. And when it does come out, it can be full of surprises. Liquid oxygen looks refreshing, but for anyone foolish enough to take the plunge, remember that it's 186 degrees below 0 Celsius. In the business of changing air into liquid, looks can be deceiving. For example, at common temperatures and pressures, water is a liquid, and air an invisible gas. But at the temperatures found in these parts, air is a liquid. Its vapor is easily seen, and water freezes solid in the noonday sun. In factories and nature alike, the wonders of nitrogen and oxygen may never cease to amaze. That's because every substance in the world, even air itself, can be a solid, a liquid, or a gas. Depending on 2 variables, pressure and temperature, matter forms solids liquids, or gases. These are the states of matter. About 150 years ago, Michael Faraday offered the first rational explanation of the states of matter. Born into poverty rather than privilege, young Faraday nevertheless entered the world of science. And once he was finally well established within the British Royal Institution, he rose to heights unreached since Sir Isaac Newton. But he soon discovered that experimenting with states of matter could be a risky business. For example, in 1823, experimenting with chlorine gas, liberated in a sealed, heated glass tube, Faraday observed a fluid forming in the cooler end of the tube. Filing the tube open to investigate may have been unwise. But Michael Faraday didn't lose his British cool. Instead, he'd found liquid chlorine. And having liquefied one gas, chlorine, he was eager to do the same to others. Perhaps too eager. But despite the pressures of his work, Michael Faraday survived. And his surviving documents prove he was the first to realize that the same matter can exist in each fundamental state: gas, liquid, and solid. But that existence would take the right temperature and pressure.
At low temperature, matter is usually solid, a state in which molecules form a rigid geometrical lattice. Although close inspection shows they're always moving, at higher temperatures, solids melt and become liquids. Now the molecules are much less orderly and flow easily past each other. Raise the temperature further, and liquids evaporate into gases. A state in which molecules don't adhere to one another, but bounce around instead. The temperature at which these changes of state occur depend on the pressure for each substance. And at lower pressures, these changes can take place at lower temperatures. Depending on the pressure and temperature, each substance is either a solid, a liquid, or a gas.
But only up to a certain point, the critical point. And above that critical point of temperature and pressure, liquid and gas no longer exist as separate states of matter. The critical point, which is a different temperature and pressure for each substance, was discovered by a Parisian physicist, Charles Cagniard-Latour. It was a startling discovery, which he made when he heated liquid ether in a sealed glass tube. What he saw can be illustrated here with liquid ethane. As the container is heated, the surface that separates the liquid from the vapor vanishes. Above the critical point, there's neither liquid nor vapor. Instead, there's one continuous fluid. As the fluid cools back down toward the critical point, striations of density begin to appear. The fluid becomes momentarily opaque because tiny drops of liquid form just large enough to scatter light. Finally, as the temperature falls below the critical point, the meniscus reappears, and clearly shows separate states of liquid and vapor. Obviously, then,
Below the critical point, gas and liquid have different densities. Above the temperature at the critical point, there's a single continuous fluid.
here, liquid never forms, no matter how high the pressure. For some substances, the temperature has to get very cold to reach the critical point. Oxygen, for example, has a critical temperature of 119 degrees below 0 Celsius. And in its liquid form, oxygen can only exist at even lower temperatures. How is it possible to cool any substance so low? And come to think of it, how is it possible for something to cool and to boil at the same time? The answer to both questions begins with the process of evaporation. And that began before things got out of hand. In fact, even before the engine was running. When the engine's cool, the water in the radiator is under ordinary pressure and more or less at room temperature. So it's still a liquid. But when the liquid boils, it evaporates. And even though it doesn't look it, the liquid also cools in the process. Cool, calm, and more or less collected, water molecules swim around slowly. Heated, they swim faster. And the higher the temperature, the faster their speed. As the temperature increases, the faster molecules manage to escape under their own power, which leaves the slower, cooler molecules left behind. At the same time, in their struggle to escape the slower liquid molecules left within, the fast molecules are slowed and cooled as they evaporate. So, both the vapor and the liquid left behind are cooled by the process of evaporation. Though on the surface there may be an air of unreality to it, the fact is, in one form or another, evaporation has kept things cool for a very long time. For example, consider Leonardo da Vinci, a genius with anything having to do with the air. He even invented a system to cool it. And for the next 300 years, Leonardo's system was air conditioning at its best. But on and on through history, scientists such as Michael Faraday continued to search for the means to get things really cold. And in the 19th century, they found it in carbon dioxide.
So, the first big step from room temperature down to low temperature turns out not to be very hard to take. And it has to do with the peculiar properties of carbon dioxide. The critical temperature of carbon dioxide is a little above room temperature. That means that if I had carbon dioxide right here in this room, but at high pressure, then it would be just an ordinary liquid. And that's precisely what I do have right here in this cylinder. The pressure is above the critical pressure of carbon dioxide, which is about 73 atmospheres, 73 times atmospheric pressure. And the temperature, of course, is just the temperature of the room. And under these conditions, carbon dioxide is a liquid. Now, if I open this valve, the pressure inside is so high that the first thing you'll hear is a very loud hiss, of course. But what's really happening is that liquid carbon dioxide is evaporating and dropping in pressure down along its vapor pressure curve to low temperature. One peculiar thing that happens to carbon dioxide is that it passes through its triple point, the point at which it freezes, while it's still well above an atmosphere of pressure. So on the way down, it freezes. It becomes what we call dry ice. And then it continues to cool. And it gets down to a temperature here which is nearly 80 degrees below 0 Celsius before it reaches the pressure of the atmosphere and stops cooling. I'd like to show you that. All I have to do is open the valve and we'll reach all the way down to minus 80 Celsius. You ready for this? It's going to be a little loud. Okay, let's see if we can cut this thing off and see what we've got. There we go. Look at that. That's dry ice. So you see, getting that far down in temperature was not very difficult. Now, as you know, once that was done, it was still a long and arduous task to get down to the temperature of liquid air. And even liquid air was not the end of the story.
No matter how long and arduous it promised to be, it was now time for Michael Faraday to set his mind to the task. The discovery of carbon dioxide was more than a dry fact in his hands. It was just the inspiration he needed to get back down to the work of liquefying gas. And later, when he found time to record his accomplishments, the scientific world took note. He had lowered the temperature of gases in a bath of dry ice and ether. And while they were cold, he had compressed them to 40 times the pressure of the atmosphere. And by doing so, Michael Faraday had liquefied every known gas except oxygen, nitrogen, and hydrogen. Liquefaction for these gases would require cooling below their critical temperatures, which is far below the temperature of dry ice. And although Faraday didn't take the next step, he had shown the right direction. A step-by-step cooling called the cascade process. Like water falling from one level to another, liquefaction takes place in a cascade of lowering temperatures, as one liquid serves as the bath for another, which then cools the next in turn. But liquefying oxygen would take another step or two, and one of the more important was the invention of the heat exchanger. The heat exchanger features two long tubes, side by side, and it starts working when cold fluid enters one end, and at the same time, warm fluid enters the other end of the second tube. And as the warm fluid flows, it meets the cold fluid in passing. Moving in opposite directions, the warm fluid comes out at nearly the same temperature as the cold fluid comes in. The reverse happens to the cold fluid, which comes out hot. Obviously, then, the fluids have exchanged temperatures. This counterflow exchange of heat, shown here by zigzags in the flow diagram, lies at the heart of the liquefaction process. Heat exchange now makes it possible to liquefy thousands of liters of oxygen and nitrogen on a daily basis. But historically, in the zigzag quest for low temperatures, while the heat exchanger was a gem of an idea, the goal wouldn't be reached without another discovery by James Prescott Joule. For a while, it looked as if Joule's luck might have been bad. Indeed, despite his discovery of the law of conservation of energy, Joule wasn't seen as a totally serious scientist. But in 1852, William Thomson, Lord Kelvin, looked upon Joule as the man who'd calculated the mechanical equivalent of heat, measuring temperature in hundredths of a degree. And in that vision, Thomson saw Joule as a worthy partner in the exciting new field of thermodynamics. And uniting his creative forces on the developing theory of energy conservation, they were able to discover the Joule-Thomson effect. When a compressed gas is heated above its critical temperature, molecules still attract each other. But that attraction isn't strong enough to liquefy the gas. However, even though there's no liquid, when the gas expands through a hole or nozzle, the principles of evaporation still operate. The molecules that escape are slowed down and cooled in the process. Today, what Joule and Thomson discovered is basically the final step in cooling and condensing a compressed gas into a liquid. But at the time, it would take one more enterprising European to turn the liquefaction of gases into a practical business. He was a very practical German engineer by the name of Carl von Linde. His process, which used only air, laid the groundwork for the future. In Dr. Linde's system, cooled, compressed air passes through the Joule-Thomson expansion valve. Gas that isn't liquefied is returned to the compressor by means of a heat exchanger, where the incoming compressed gas is cooled to a lower temperature by the outgoing cold gas. And the net result is liquid air. But from a scientific point of view, even liquid air is not the end of the story. At the point at which liquid air, that is liquid nitrogen and liquid oxygen, were first made, it was realized that there was one remaining gas whose liquefaction point would be the lowest temperature of all. That gas was hydrogen. And it was also realized that whoever liquefied hydrogen would have made a great scientific triumph. And so once again, the race was on. One starting point was the scientific playing fields of England, home of the Royal Institution, which might have had an edge to begin with. After all, these cool British halls were the intellectual stomping grounds of Faraday, Crookes, and Davy. Sir James Dewar earned his title here. And here, too, lingered the extremely competitive ghost of Isaac Newton. On its picturesque surface, the Netherlands hardly seemed an advantageous starting point. But Holland is the land of the University of Leiden. And not only did these walls already echo the scientific legends of Musschenbroek, von Marham, and Boerhaave, this wall, perhaps the most noteworthy guest register in scientific history, would reflect world-class scientific achievement for decades to come. But in the 1880s, long before Lorentz invited Einstein to lecture here, the race was still on to liquefy hydrogen. And in the physical laboratory of the University of Leiden, when it came to liquefying the last remaining gas known to science, the leading candidate was the distinguished professor, Heikki Kamerlingh-Onnes. Across the English Channel, however, the smart London bookmakers would have put their money on Sir James Dewar. Certainly he'd become an authority on the liquefaction of gases, and on any given Friday, he'd be able to stand up and explain precisely why. At the Royal Institution, in addition to being an inventive lecturer, Dewar invented many things of scientific note. Among other things, a variety of double-walled containers to keep fluids cold. In scientific circles, these handy little inventions became known as Dewar flasks. Today, they're more commonly called thermos jugs. In any case, With their help in 1896, James Dewar won the race. He was the first to liquefy hydrogen. Nonetheless, in one of those strange twists of scientific history, he didn't liquefy the last known gas. Right at what was supposed to be the finish line, an entirely new gas was discovered. It was helium, which would have the lowest liquefaction point of all. And for Kamerlingh Onnes, helium was another opportunity. He immediately set out to be the first to liquefy what was now really the last gas on Earth. It took extensive scholarship and extraordinary machinery. It took capable assistants and over 10 years. But it was a success. Kamerlingh Onnes was the first to liquefy helium at a temperature of only 4 Kelvin degrees above the absolute zero. His achievement was not only amazing for its time, it opened scientific frontiers that are being explored to this very day.
Now, liquid air is not nearly as cold as liquid helium, but it's still plenty cold for most purposes. For example, it can change drastically the properties of ordinary matter. Let me give you an example. I have here a light bulb which is now being lit by current that passes through this copper wire. And the copper wire has a quite high electrical resistance, and as a result of that, the bulb is barely glowing. In fact, you can't see it glow at all, but I can see from here that it's just barely glowing. But if I take this copper wire and put it in liquid air, its electrical resistance will decrease by so much that you'll easily be able to see the bulb start to glow. Watch this. There are lots of other things that you can do with liquid air as well. For example, people tell you to put flowers in the refrigerator. Well, the extreme cold of liquid air really isn't very good for flowers. Let me show you. Interestingly enough, it doesn't change the way the flowers look very much. When I pull them out, they look pretty much the same, but it has made them just a little bit brittle. Now, there is one more thing I would like to try at this temperature, and that's a football. You know, people do play football games in these incredibly cold climates, like Green Bay, Wisconsin, where the temperature can be 40 degrees below zero. And I often worry about that. I don't worry so much about the football players. After all, they get paid plenty for doing that. And I don't worry about the fans, because anybody who would go to a game on a day like that deserves exactly what he gets. And I don't even worry about the sportscasters, because they're probably inside of a warm broadcast booth behind a plate of glass where they're perfectly safe. What I really worry about is the football itself. Because it does seem to me that being that cold can have an absolutely shattering impact on a football. All right, don't take any wooden footballs, and I'll see you next time.
Funding for this program is provided by Annenberg CPD to advance excellent teaching. For information about this and other Annenberg CPD programs, call 1-800-LEARNER and visit us at www.learner.org.